There we go. All right. So for those of you coming in late, 7.6, we're looking at number 7 here. This was the differential equation, initial conditions, and we're given that my function on the right-hand side only exists between 0 and 2 pi. All right. So far, we took the Laplace of both sides, where the Laplace of the second derivative, just writing it out using the formula here for the properties is that. That's going to be plus 36 times the Laplace of the function I. And then that's going to be equal to the right-hand side, where the Laplace of the right-hand side, we only really care about it between 0 and 2 pi. So we just have to be careful about what the Laplace is going to be. It is not going to be just looking at this table over here, because this would be the table if we're looking at the entire function 33 sine of 5t. Here we're only looking at it between 0 and 2 pi. So this is where those special kind of u functions are going to play a part. So maybe what we should do is let's kind of come down to scratch paper and let's worry about what the Laplace of that function g is going to be, where g is this function here, 33 sine of 5t between 0 and 2 pi, and then 0 where we are bigger than 2 pi. Okay, so to do this, I'm checking my notes because I want to make sure I get this exactly right. This is that u stuff. I want to make sure I get the u stuff in the right order. Otherwise, I'll look silly.
We can hear her whispering.
Yeah, my mom is being silly, sorry.
Here we go. This is what I'm looking for. So this is the thing that we're going to be using here. So the formula that we're using is that the Laplace of a function f of t minus a times u of t minus a is equal to e to the negative as times the Laplace of the function. So this is kind of what we're using to solve this Laplace of g. I guess these should be curly brackets here. It's just that we want to think of g as being the function here that only exists between 0 and 2 pi. Okay, so I guess we could rewrite out what g is going to be. Like g of t is going to be that function, 33 sine of 5t, multiplied by that u function of t minus 2 pi. Does that look right? Am I crazy? Like I said, it's been a while since I've looked at this stuff.
It had me do some weird stuff at the beginning of 7.6 where it was like instead of like the 5t, it'd be 5 parentheses t minus or whatever.
We don't have to do that here because we are starting at 0. Like we don't have to shift this one because it's already starting at 0. Maybe what we have to do is to shift it 2 pi to the left so that this is at 0, but I don't think so. I think we're good. Let's see what the example says. I just don't want to steer you guys in the wrong direction like I've done in the past. Yeah, so this is what I was a little bit worried about. We don't want to use just the u function right away. We want to use this pi function. So to draw on the screen here to show you what this is saying. Oh, you know what I could do instead? Let's look at Desmos. All right, forget drawing on the screen. Let me pull up Desmos.
Bet you miss having Maple.
I do, very much so. This would be a lot easier. Oh, maybe Desmos is easier. It's just that I'm so used to something like Maple. So we had the function 33 sine of 5 x, I guess. So it looks awful, right? Like it's huge, and then the period is very, very big. But we only want this. Like, how do I add restrictions for the x?
You have to go down one and say like y equals or x equals.
Could I do like 0 is less than or equal to x is less than or equal to 2 pi? Well, kinda.
You might be able to put it on the same line if you separate it with a comma, maybe. Maybe not.
I did not like that.
You still have Coke out.
Yeah.
That's true, I do. I mean, this is good enough. It's okay. The problem is that the graph's very big. But just know that we're only looking at these red sine waves in between this blue line here. Like, that's the only part that we care about. Other than that, the function is going to be 0 everywhere else. So it's a flat line at 0, and then it jiggles up and down here, and then it continues to be a flat line at 0. When we are looking at those u functions, these u functions that we're dealing with are going to be of this kind of form. So u of t minus a is that at the point A, that is when it jumps up to be 1. Everywhere to the left of A, it's at 0. All right, so it's 0, and then at A, it jumps up. What we're going to have to do is to combine two of these together, and that's that capital pi thing that you probably saw in the notes. I don't know if Desmos can graph that kind of stuff. Let's see. Desmos unit step function? Maybe it can. Looks like it. Oh, that's so cool. Okay, so what we want to graph is we want to graph, what was it, 33 sine of 5t times this u function, u minus 2 pi. It doesn't like it. Use parentheses around the argument of sine.
It's your variables. It should be a t minus 2 pi.
Ah, perfect.
Or x there.
Yeah, x.
Whichever way.
Okay, so if we just try to do this, which is what I was trying to do in Word, notice that it's not quite what we want, right? This is 0, and then we hit the 2 pi, and then it jumps up forever. So really what we want is we want this, where it starts at 0, but then it has to stop. So then we're going to subtract 33 sine of 5x, u of x minus 2 pi. So now what we get is it's 0, and then in between 0 and 2 pi, it's the sine function, and then it's 0 everywhere else. Does that make sense on that's what our function g is?
Yeah.
All right, so that means that over here, I need to rewrite this. Our function g is really this. 33 sine 5t times the u function starting at 0 minus 33 sine 5t, the u function starting at 2 pi. All right, so that's the function g rewritten using these u's. And now also we're using this property to figure out what the Laplace transform of g is going to be. So we'll just do each of these separately. All right, so first, because of this u of t minus 0, we're going to have an e to the 0 out in front, which is just 1. So this first property is just going to be whatever the Laplace transform of 33 sine of 5t is, and we'll figure that out in a second. But that's going to be minus this one. The Laplace transform of this whole thing, because of this u t minus 2 pi, we're going to have an e to the negative 2 pi s out in front. Oops, pi s. Times the Laplace transform of whatever 33 sine of 5t is. Okay, is that part okay, just using the definition or the property up top here? Everybody still with me?
Kinda.
The only thing I'm a little bit worried about is this t minus a. I think you're right. I think we do have to shift stuff. Not for this first one, because I think this first one is okay, but the second one we may need to shift. Like this may need to be a plus 2 pi, no, like a t plus 2 pi inside, like that. That way, if I do plug in t minus 2 pi into this, I still just get the t as a replacement. All right, I'm thinking here for a second before we continue with that. Let me double check my notes here.
tried reading the check and the book just spoke math, so...
I'm just double checking.
I don't think a person becomes fluent until their master's degree in math.
Not even then for this stuff. No way. It still takes me a long time of going through it to make sure that I have it all written out correctly. So the problem is that the example that I went through, the example that I made the video about, is that it didn't have a function over here. Like it was just the thing as is. All right, so we'll keep going. We'll keep going like it is, because I think this is right. Because the a is 2 pi. And then we have to substitute this in for here to undo it. Give you an example?
The example's doing the same thing you're doing. For the most part. Then somehow it brings in like h of t.
So it does not do this part. It just leaves that as 5t. It also doesn't find the Laplace transform of all this stuff right away.
There's a lot of dots.
Oh no, they do this part. T plus a. So they do the t plus 2 pi being plugged into there. Let me just keep going here, just to double check. Yeah, right there. Okay, I'm leaving it like I had it. All right, no more second guessing. We're just going to go with what my gut. Sorry. We'll leave it like that. So we have to plug in the t plus 2 pi here. That way, when I do plug in t minus 2 pi in for this t, the 2 pi's cancel, and I get back just the regular 5t. Okay, they do a bunch of like skipping around and stuff, but let's go ahead and write out what this Laplace transform is going to be before we plug it back into the differential equation. So this is where I'm going to need those properties or the table over here. So when I do have a sine of something, the Laplace transform is this. So whatever the b is goes up top, and then the b squared there on the bottom. So 33 sine of 5t is going to be the 33 out in front, and then 5 over s squared plus 25 in the denominator. So that's the Laplace transform of this first one. That's going to be minus e to the negative 2 pi s. And then again the Laplace transform, but this time it's going to be a little bit different. What's really nice about this is that if I do multiply the 5 into this, it's going to be 5t plus 10 pi. And I'm pretty sure that that is periodic. It's the same thing as just sine of 5t. Does that make sense on why that's the case? All right, because sine is periodic with 2 pi. So adding any multiples of 2 pi inside of sine is not going to change the value any. So I think this is also going to be 33 and then 5 over s squared plus 25. Again, we're going with our gut here. Okay, is that part okay? Questions about that?
I think it makes sense so far.
Okay, cool. All right, now back to the differential equation. So this thing that we're starting with up here, we still have the s squared. The Laplace of I minus the 5s minus the 21 plus the 36 Laplace of I. So that's just copying down the left-hand side that we had before, and that's going to be equal to this right-hand side that we just found. Okay. Now what we need to do is to again solve for the Laplace like we were doing it before. So we'll combine the s squared and the 36 as the coefficient, move everything else over. So this will be s squared plus 36 all times the Laplace. and that's equal to, and then a bunch of crap over here. Cool. So I was trying to think of like a good way to simplify it down, and I don't know if there is a good way to simplify it down. Maybe what we can do is we can multiply the 33 and the 5 together for now. 33 times 5 is something.
165.
So we'll do the 165 over the s squared plus 25. And then we're factoring that out, so we'll be left with 1 minus e to the negative 2 pi s inside the parentheses. Then we are also adding the 5s and adding the 21 over from the left-hand side. Okay, now what we want to do is go ahead and divide this over, and then we take the inverse Laplace transform, which looks ugly, like really ugly. So I'm curious if there's a trick that we can find here in the properties. It looks like the trick's going to be this part right here, because we're still going to have some e to the negative s stuff, which means that when you do the inverse, you're going to end up with some u's, which is okay, like here, this line. So let's try to get everything together that does not have the e, and then everything that does have the e, and kind of break it down and see what we get. I'm going to go through the view and example again, just so I can kind of get a heads up of what to do with this part.
Yeah, it kind of sucks how most of these don't have any correlation from the initial problem to the answer.
Right. So you can kind of see that that's what they did the part that we just did, right? They broke it up into the term with the e and without the e. So let's see what they do next. I'm pretty sure they just leave this one alone and then combine all the others together, which does look like what they do. Okay, so let's do the same thing. We need to combine all of the terms that do not have an e in them and leave the ones that do have an e alone, which kind of means that I'm going to have to multiply this thing back out. So let me just rewrite this out, and I'll maybe once you see it written out, it'll make more sense of what we need to do. Okay, so I'm just going to leave the one with the e in front. So we have that 165 e to the negative 2 pi s over the s squared plus 25. So that one's out front. Oh, it's negative, sorry. So there should be a negative sign. Everything else we have a plus 165 over the s squared plus 25. And then we have this one, the plus 5s, but I'm going to make it to have the same denominator. So I'm going to write it as 5s times s squared plus 25 divided by the s squared plus 25. And then the same thing with the 21. So plus 21 s squared plus 25 divided by the s squared plus 25. All right, now these last three fractions, we're going to try to combine those, the numerators all together. And I'm going to go ahead and do that and divide by s squared plus 36 all in the same go. So on the left-hand side, all we're going to have is the Laplace. On the right-hand side, we're going to have this first term, the one with the e in it. And on the denominator, we're going to have s squared plus 25, and we're going to have s squared plus 36. Okay, plus all of these are going to combine into a single fraction. So let's try to keep everything straight. It's just distributing here. We are going to have an s cubed coming from this term. So we're going to have a 5s cubed that's all the way out in front. That should be the only s cubed term that we have. We're going to have an s squared term. It looks like the only s squared term we're going to get is from this 21. So plus 21 s squared. We'll have an s term coming from this, the 5s times the 25, so a plus 125s. And then we're going to have a constant, two constants, the 21 times 25, and then the 165 out in front there. So I'm going to use a quick calculator in my phone to see what we get from that. I got 690. All right, and then that's still all divided by combining all of those fractions together. We get the s squared plus 25, but we also divided over this coefficient, the s squared plus 36. Okay, great. So is everybody still with me with this? I hope.
So you just distributed your numerators and then combined them, pretty much?
Yes. Yeah. Okay, next, partial fractions over here. We cannot do partial fractions here unless we take out that e thing. But if we take out the e thing, which we may have to do and then do partial fractions for it, now that I'm looking at it, I think that is what we're going to have to do. So just going back to the view and example, yeah, they break it down so that it's the partial fractions of both. So they do the awful one, the big one. No, they leave that one as is. Let's see what they do next. Yeah, and then they do partial fractions for that one too. Okay, great. So partial fractions for both terms. Ew. So let's look at this big one first. I'll just copy it down. I have the luxury of copy paste. Because both of these denominator factors are unfactorable, unfortunately it's going to be two fractions here where both of them are quadratic, which means that the numerator needs to be linear. So we're going to have an as plus b up top, and then the factor s squared plus 25, and then a cs plus d over the other quadratic factor, s squared plus 36. Irreducible was the word I was trying to think of. Like, you can't break those down. Multiply both sides by the common denominator. We end up with a 5s cubed plus 21s squared plus 125s plus 690, and that's equal to the right-hand side. We're going to end up with the as plus b. That one times the factor s squared plus 36 plus the cs plus d. That one, oh jeez. Times the s squared plus 25.
So where did the s squared plus 36 come from?
S squared plus 36 came from the left-hand side of the equation.
Okay.
And from up top here, that was just combining the two terms that had the Laplace in it. So we divided it over. All right, and now you want to do whatever you do here to find the A, the B, the C, and the D. It looks like the easiest one to do here would be to multiply these out and then do the whole coefficient thing. So just foiling both of these sets together real quick. Well, not real quick, but quick-ish. Okay. All right, so this was just that right-hand side all factored out. And now we could set the different power function coefficients equal. Let me come down here. So we have the s cubed functions. We have a 5 on the left, and we have an a plus c on the right. We have the s squared coefficients, 21 on the left, b plus d on the right. Just the linear stuff, s, we have 125 on the left, and 36a plus 25c on the right. And then we have the constant terms, so we have 690 on the left, 36b plus 25d on the right. I don't think I missed any. Okay, and then we solve this, like however you feel comfortable solving. Looks like substitution will be the easiest. This first equation, I could solve for either A or C and plug it into the third equation. This one, I could solve for either B or D and plug that into the fourth equation. So maybe this first equation, we'll just solve it for A and get A is 5 minus C. And then if I substitute that into the third equation, I get 125 is equal to 36 times 5 minus C plus 25C. Solving this one, multiply the 36 into there. Figure out what 36 times 5 is. 180. Minus the 36C plus the 25C. And then, so just combining like terms together, we can subtract the 180 over, which is going to give us negative 55. And that's going to be equal to, this looks like it's going to be negative 11C. In other words, C is 5. We were so close to getting that on one line. Oh well. Okay. And now if C is 5, that means if I plug it back into here, we get A has to be 0, which is fine. Same thing for this next set of equations. We'll solve it for maybe B and get B is 21 minus D. Plug that into the last equation. That's going to give us 690 is 36. I missed a letter here. 36B plus 25D. So 36, 21 minus D. That plus the other one, 25D. Okay, and then again, we would use some calculator stuff to answer this one. I get negative 66 on the left-hand side, and then I get plus 11 on the right-hand side. In other words, it looks like D has to be 6. And then if D is equal to 6, then B has to be 15. Okay, I hope that's right. It looks decent enough. They're at least whole numbers.
I think it should be a negative 11.
Ooh, okay.
Because when you distribute 36, that's a negative.
You're right. So this is really
But
a...
that'll still give us a positive.
Oh, yeah, you're right. Sorry, I was doing it in my head and didn't write it out right, but good catch. Okay. All right, so what all of this means... oh, you know what? Before we even figure out what this means, let's go ahead and do the partial fractions of this other one. So the other one that we're looking at is the one that has a negative 165 above the s squared plus 25 times s squared plus 36. We want to ignore the e thing because we're just going to leave that e thing multiplied on the outside of my fractions. Okay, so does everybody see where we are? Taking this other fraction, negative 165 over those two irreducible things. Hopefully this one will break down a lot nicer, but I guess it doesn't have to. So we're going to start all over. We're going to have a linear term, as plus b, that over the s squared plus 25, plus the other linear term, cs plus d, that one over the s squared plus 36. Multiplying both sides, we get negative 165 on the left. And because we already multiplied out the right-hand side up top here, I'm just going to copy it down. I hope you wrote it all out and still have it. I'll let you guys kind of catch up before I move on from this. But notice that it is the same right-hand side all multiplied out, which is nice. Okay, so now the same thing. We're just going to set the stuff together. So we have s cubed terms, 0 on the left, and then a plus c on the right. S squared terms, 0 on the left. B plus D on the right. Just linear terms S, 0 on the left. 36A plus 25C on the right. Constant terms, negative 165 on the left. 36B plus 25D on the right. And again, you can solve these however you want, substitution, matrices, whatever you want to do here. Substitution is probably the easiest. This one gives me A has to be negative C. The second one here gives me that B has to be negative D. So if I plug that into this one, I can already tell you that they're both going to have to be 0, but just to plug it in to show you, we get 0 is equal to 36 times negative C plus 25C, which is 0 is negative 11C. In other words, C has to be 0. And then if C is 0, that means that up top here, A also has to be 0. This other one's not going to quite be the case. So for this other one, if I plug in B to be negative D, I get negative 165 is equal to 36 times negative D plus 25D, which is negative 11D. And then 11 goes into 165, I don't know, some number of times. 15, I'm guessing. So D is 15. Okay, cool. And then if D is 15, that means that B has to be negative 15. All right, I know I did these kind of quick. Just take your time with it and get it right. All right, now all of that is to say that now the Laplace transform of I is the first partial fraction had that e to the negative 2 pi s, which we're going to leave out in front, times the partial fraction decomposition, which was as plus b. So we're just going to have the negative b, the negative 15, over that s squared plus 25. This was up above a little bit. That plus the cs plus d, which is just going to be the d positive 15 over the other one, s squared plus 36. Okay, so that was the first partial fraction decomposition, the one that had the e up top. That's going to be plus the other partial fraction decomposition, which was a little bit uglier. So that's coming up to these coefficients of the a, which is 0, and then the b was 15. So we're going to end up with 15 over s squared plus 25. I guess that's a little nice. Similar to the other one. Plus the cs plus d, which is 5s plus 6. That over the s squared plus 36. Okay, so there you go. That's the partial fraction decomposition of those two separate fractions that we had. And now, hopefully, these will match up with some of the table stuff from over here. It definitely looks like most of them do. So for this first term, it's constant up top, and then over s squared plus 25, that's going to be a sine function. This one, same thing, another sine function. This one's going to be a sine function. This one isn't quite a sine function, but what we can do is we can break it up into two separate ones. One that has the 5s up top, and then one that has the 6 up top. So just to rewrite this whole thing, but breaking up that last one because it needs to be broken up. This we're going to leave the first one to be 5s over it, plus we're going to have a 6 over it. Now this one is going to be a cosine one, this one's going to be a sine one. The last thing to worry about is to make sure all of the coefficients match what they need to match over here to do the inverses, but we also have to worry about this e thing out in front. That e thing out in front is coming from the other table of properties down here, is that anytime you do have an e to the negative AS multiplied on a Laplace transform, then you just do the inverse, but with t minus a plugged in, and then you multiply by that u t minus a. That's that function that splits it up to start at a. Okay, so here we go. That means that my current I is going to be the following. Negative 15, let me go back to the other table here. The negative 15 s squared plus 25 is going to be the sign, where my b has to be 5. And if my b has to be 5, that means I have to factor a negative 3 out of this to make the numerator to be 5. So negative 3, and that's going to be sine of 5t. But because of this e, this is going to be multiplied by u times t, not times, sorry, u of t minus 2 pi. And I think I have to be a little bit more careful here. And the reason I need to be a little bit careful is going back to this table of properties over here. So when you do the inverse Laplace of a function that's in this form, the e to the negative s f of s, really it's going to be the inverse Laplace, but plugging in t minus a. So it looks like instead of just a 5t for the sign, it's really going to be 5t minus 2 pi. Oops. Okay, so I want to make sure this makes sense before we move forward. So it's coming from this identity here, this line. If you have the e out in front, that's going to make this u appear at the end. That's what chops off your function. But it's not just the inverse Laplace, it's the inverse Laplace plugging in t minus whatever that coefficient a is from the exponent of the e. So we have to plug in t minus 2 pi into my sine of 5t. Is that one okay before we do the others? Kinda?
Kinda, mostly.
Okay.
Plug in the formula.
Same thing's going to happen here. We have the e. This, we need to be a 6 up top, right, to match the b squared in the bottom. So to make that be a 6 up top, I'm going to pull out that 15. I'm also going to pull out a 6 in the denominator. That way it becomes a 6 in the numerator, and we end up with a sine of 6t. But it's not just t, right? It's t minus 2 pi. And then that has to be multiplied by that u function, u minus 2 pi. U of t minus 2 pi. And 15 over 6 reduces down, doesn't it? Well, I'm going to leave it like this just so maybe people will see where that's coming from. Pulling the 15 out, but you have to force the 6 to be up top. So you have to pull a 1/6 out.
It does reduce down to 5/3.
Okay, cool.
Or 5 halves.
5 halves, yeah, okay. I'll just go ahead and replace it in there now. Okay, that was just the first 2 terms. We still got 3 more here. But these should be a lot easier. So this one, we have to have a 5 up top. So I'm going to pull out a 3, and then we're going to end up with sine of 5t. We do not have to worry about a u function here because there's no e multiplied on this one. All right, that's going to be plus. This is going to be a cosine one, right? So just going back over to my table. Whenever you have the s in the numerator, it's the cosine one. So we pull the constant out, and then my b for this is going to be 6. So we're pulling the constant of 5 out, and then it's going to be cosine of 6t. And then the last one is another sine one, so plus. It already has the right numerator, so just sine of 6t. All right, and that's it. So that should be the right answer that we want to plug into here. I did not open this up in my teacher cheating one, so I don't know what the right answer is. And I don't know if I really feel like plugging all that in. I guess I will, just so we can get that green check mark. Hopefully. All right, so it was -3 sine of 5t minus 2 pi times u of t minus 2 pi, okay, plus 5 halves sine of 6 times t minus 2 pi, u t minus 2 pi, plus 3 sine of 5t plus 5 cosine of 6t plus sine 6t. Oh, whew! We did it!
Yay.
Okay. Yeah, so these are long, right? Just as obnoxiously long as the section 5 ones. So just make sure you're kind of prepared for them using this process here. But it's the same process as before. It's just you're adding in these extra u's.
Can you go through the U's one more time? I'm sorry.
No, it's fine. So the u's are all based on the right-hand side over here, this g function that only exists between 0 and 2 pi. So we want it to be this function between 0 and 2 pi, and that's what these g functions are doing. Where was the one? There it goes. So here, 33 sine 5x u of x minus 0, if I just leave that part in there, this is going to be the function of 33 sine 5x that starts at 0. The other one I had was y equals 33 sine 5x, but this one was starting at 2 pi. So notice that's the purple one here. So what we were doing is that we were actually taking these two things and subtracting them. The 33 sine 5x where it starts at 0 minus the 33 sine 5x that started at the 2 pi. Because when we do that, we only get the section of g in between 0 and 2 pi, the part that we care about.
Okay. Wait, so are the U's not like the union thing? Are they different U's?
They're different U's than the union thing. This just stands for a function. What this stands for is it just tells you that the function starts at that location. There is a formula for it, but it's not like a fun formula. Let's see if I can do those weird things. It's one of these. So it's 0 when t is less than a, and it's 1 when t is greater than a. So that's my function u. Oop. So basically when you multiply this onto another function, it just makes it so it's 0 everywhere, and it starts at the location A. But what's interesting about it is that when you do that, the Laplace transform lets it behave somewhat nicely. I know it looks ugly, but this is actually pretty nice compared to what it could be if we tried to solve this a different way. What I think would be really interesting is let's plug this into Desmos and see if Desmos can handle it. And we can kind of explain what's happening. Oh, I didn't like it. Sorry, I don't understand the quotation symbol.
Oh, you have to replace the t's with x's.
Oh, okay. Good catch. X. 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 Come on, you.
It probably doesn't understand the u's.
No, because we defined the u's up top here. Like we had just defined. Maybe I need to write it all out instead of just copy pasting it. All right, so it was coming from this. -3 sine 5 times t minus 2 pi times u t minus 2 pi. That was plus 5 halves sine again of 6 times t minus 2 pi times u of t minus 2 pi. That was plus 3 sine 5t plus What was the next one?
5 cosine of 6t.
5 cosine 6t, and then just plus sine t, right? Sine of 6t.
6.
There we go. So this is what it looks like. All right, don't worry about anything that's happening before 0, because that doesn't matter. And then remember, we're looking at a circuit, okay? And this is the circuit that has this as the initial input of voltage. So when you throw in this crazy voltage, your circuit struggles trying to find a resting point or an equilibrium because the input is so crazy. But after it filters it all out and after we stop the input, it settles down on like a nice sine wave. Pretty cool, right? Like here's your input of electricity. The circuit's trying to figure it out here at the beginning, but once you stop the input of electricity, the circuit then settles down at an equilibrium. And remember the I that we're talking about, the blue line here represents the current.
That's pretty cool. Yeah.
Okay. I know these questions are long, and they're hard. I do get that. I promise that on the test, there's not a lot of these. At all. The majority of the questions on the test have this kind of stuff, but broken down. Like maybe it would just say to solve for the Laplace transform. If you were solving for the Laplace transform, you could have just stopped it here, right? Once you had the Laplace on one side by itself. Other times, I may just give you something like this and then ask you to find the inverse. So that would just be these little lines here. You would do the partial fraction decomposition and then find the inverse based on that. I think there's only 1 or 2 questions on the test where you have to do the whole thing all the way through, like some of these homework questions are. But does that help with this question? Is there any other concerns or of any of the steps here? Okay, do we want to do another one? That one took an hour.
Can we do 7-7 stuff? Or
Yeah, let's look
like
at
7-7?
let's look at some of those. I don't think the 7-7 ones are long like that one is. Not necessarily. Maybe some of them are.
Just explains it really weird.
A specific one?
I haven't done any of them because I couldn't understand what the book was saying.
All right, let's look at number 1. Determine the Laplace where f is periodic with the given period. Also graph f of t. So f of t is just 2t, but it's saying that it's periodic with a period of 1. So going to Desmos real quick. Come on, Desmos, where are you? Not that stuff, I guess. We'll just look at this stuff. So if we just graph the function 2t, y equals 2x, I guess, for us, it's this crazy diagonal line, right? But what we're saying is that we're going to stop it at 1 and then just have it repeat that process forever and ever and ever. And I don't know of like a really good way of graphing that. Let's see if Desmos can. Desmos periodic functions. I hope it's not just trig stuff. I mean, trig stuff is definitely periodic by nature, but we don't want the trig to be periodic. Or we don't want trig here. And that's not going to help us. Let's see what else it's got. All right, forget it. It's this, right? I don't want to spend too much time in what this is going to be. The graph of this one, if it has a period of 1, is it's going to be the normal diagonal line here that only goes out to 1. But then it's just going to repeat that diagonal that line from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and so on and so forth, right? This is going to be the graph of this. The function f of t from 0 to 1 with a period of 1. It takes that graph and it just repeats it forever and ever and ever. Does that make sense?
Yeah.
Okay. So what we want to do is we want to figure out the Laplace transform of something that's repeating like that. And it's important to do stuff like that, going back to physics again, because not every wave that we have is like a perfect sine or cosine wave. I'm sure you've seen the AC or DC, I forget which one is which, but there's waves that are square like this, right? Or maybe they come down like this. You know what I'm talking about, yeah?
Yeah.
Okay. So the only way of defining those is going to be kind of this weird periodic way. And then I think on the homework, it gives you those tables again. Oh, no, it doesn't give you the tables. In the book, it gives you some formulas. And this is the formula that you really need to worry about. Here. So when you're dealing with periodic functions and you're trying to find the Laplace transform of the periodic function, you're doing this. So we label a periodic function like this, f with a sub t, where that t represents the period. So here the t is really going to be represented by 1. So this is my function over here. Or this is the Laplace transform of this. I guess you can think of this as the Laplace transform of f of little t, like that. Same notation here. Okay, anyway, this Laplace transform of the function we're trying to find over here is just this. Double checking my notes here. Yeah, it's just the integral from 0 to that period t, e to the negative st, and then the function of t dt. So this is just kind of like the basic definition for it, because this is the only location it's going to exist on that kind of thing. All right, so that is what we call the Laplace transform of just the one period. If we want to find the entire Laplace transform of my function, that comes from this formula. It's the Laplace transform of just the one period divided by 1 minus e to the negative st. All right, this is like kind of the end-all be-all when it comes to the formula of what you guys need to know from section 7 here. Okay, so again, the total Laplace transform of the entire function that keeps repeating forever and ever and ever and ever is the Laplace transform of just one period of it divided by this term. Okay, so for this example, we're going to need the Laplace transform of 2t, where my t is bounded from 0 to 1. We have to do the integral form for this. So we're going to be integrating from 0 to 1 e to the negative st times 2t times the function. That's coming from this formula here. That's the definition of the Laplace transform, remember. All right, you just have to do this. So you can pull that 2 out. And then other than that, or I guess we could leave the 2 in, but it has to be integration by parts. So we'll let u be the 2t, dv will be the e to the negative st, which means du is 2 dt, and v would be negative 1 over s e to the negative st, the antiderivative there. Okay, plugging all this in, that's going to be u times v, negative 2t over s e to the negative st. This is going to be going from 0 to 1, but we'll worry about that in a minute, minus the antiderivative of v du, which is negative 2 over s e to the negative st dt. The double negatives cancel, so really this is positive, and also the 2 over s is just a constant that we can pull out to the front, because remember we're integrating with respect to t. So we still have this first term. For this term, oh, I forgot my negative up top here, sorry. That should be an e to the negative st here for the exponent. So the antiderivative of just that part, remember it's positive now, and we already have a 2s, 2 over s, but now we're going to bring down another negative 1 over s, and then the e to the negative st just stays. All right, now we need to evaluate this between 0 and 1. So we're going to plug 1 in for the t's first. That's going to give me negative 2 over s, e to the negative 1, or not negative 1, sorry, negative s, minus 2 over s squared, e to the negative s. Then we have to plug 0 in for the t's, so it's going to be that thing minus plugging the zeros in for t. This first term is just 0 because of the t out in front here, minus 1 over s squared, and then the e to the 0 is just 1. So finally we can kind of combine all this stuff together as best we can, and I don't know if there's a good way to even combine all that together.
Your exponent in the first one, the second set with the e, should that be an e to the negative s as well?
You're right, that should be a negative sign up there. Okay, now remember, this is not the final answer, right? This is just the Laplace transform of one period. Now we need to take this and put that in the numerator and then divide that by 1 minus e to the negative s. And this is t is going to be a 1 up top here. So finally, we get that the Laplace transform of my function f of t is the following, right? So it's that thing that we just had divided by the 1 minus thing. So just copying this down. And then in the denominator, 1 minus e to the negative s. Again, because the period t is just a 1. Maybe there's a way to simplify this down so it looks a little bit nicer, but I wouldn't even bother. All right, I hope that was right. That sounded good. It doesn't have a textbook thing. I'll just get it wrong a few times and we'll see what it is. I'm a little bit worried that the answer is going to be like so complicated it's not going to look like what we have. And it kind of does, right? Like what we have simplified down is probably that. Great, yay. I can tell just by looking at it that it does look like it would be. Because it looks like what they did is they factored the terms that have the e to the negative s together and combined the like terms. And then you have to multiply everything by s on top and bottom to make that s show up here. And then the 2 over s squared just kind of comes out because you're going to end up with a 2 times this 1 minus e to the negative s, and it'll cancel out top and bottom for the first fraction, but not the second fraction. So I think we're right. There is another part to this. And that's just asking for the graph of the original function. Remember that was this one, right? It's just that 0 to 1 thing over and over again. Yep. So I hope that helps with this one. Again, the hard part is knowing which formula to even look at from section 7, and the formula is this. Where remember the numerator is the Laplace transform, but just for one period. You have to do this integral to figure out what that numerator is going to be. There's no way of getting around it. You can't use that table that we had from before. Okay, so does that help you at least get started here on section 7? Remember, this stuff's not due till Wednesday next week, so we will meet next Tuesday, which I know it's the day before, but we can look at some more of these. And if you guys do have some more questions from these, just send me an email and ask, and I'll either write something up in Word or I'll make my own special video solving these questions. One other thing I want to say before we get going, though, is the final exam stuff. So I think I put up a practice thing already, right? Does that sound familiar?
Yeah, it's up.
Okay. Yeah, so I put this up. I would really like next week for us just to kind of focus on doing some of these final exam practice stuff. But of course, I'm not opposed to doing some extra Chapter 7 stuff on Tuesday. I would also like to have an additional day, but I don't know what day that could possibly be because I don't really want to do it over the weekend, but I don't mind doing it over the weekend. Remember, the final exam itself is going to be due on that Monday, May 11th. So what I was thinking is that I know that you guys have the Chapter 7 test due for next Wednesday. Would you guys be up for a Monday afternoon one at 6, or even a Friday afternoon one at 6?
Yeah, that works for me.
Yeah, I'm good for either. I think Friday might be better just because we'll have the Chapter 7 stuff taken care of.
Yeah, I kind of like that. So on Tuesday next week, if you guys want, we could just focus on Chapter 7 to get ready for that test on Wednesday. But then we can do 2 sessions, one on Thursday and one on Friday, that is just preparing for the final exam, which is happening that Monday.
Yeah, the final sounds like a nightmare.
Yeah. Okay. So that'll be our plan then for next week. So Friday afternoon next week. Don't make any big plans. I mean, you can if you want, but I'll be around. I won't make big plans.
We're going to keep 7.5 off the final, right?
7.5 is definitely going to be on the final. Definitely one question.
I've tried.
Any last questions about just like a quick what's going to be going on for us the next 2 weeks?
Do you have an idea of the time on that Friday? Would we still keep it at 6 or?
I think so, just because that's what we've been doing so far. Yeah, 6 on Friday.
Yeah, that works for me.
Okay.
How many questions is going to be the final?
I'm planning for it to be about the same number of questions as the Chapter 7 test, which I think was, what was it, 10 or something like that? Let me just double check.
It's 10.
Or was that the
10.
No, the one before was 8?
Yeah.
The Chapter 5 was pretty short, yeah. I'm looking at anywhere between 10 to 12 questions for the final.
It's mainly going to be focusing on what chapter?
The final is mostly going to be on Chapter 4 stuff, since that's what we spent the most time on. It's been a long time since we looked at Chapters 1, 2, and 3. You'll have a couple of questions kind of dotted in between those. The majority of questions coming from Chapter 4, maybe 1 or 2 questions from 5, maybe 1 or 2 questions from 7. All right, anything else before we go?
No.
Okay, I appreciate you coming. Of course, if you have questions, again, just email me, and then we can look at some more of this Chapter 7 stuff on Tuesday next week to get you guys ready for the Chapter 7 test. But thanks for coming. I'll see everybody next week. Have a good weekend.
Too, thank you.
Thanks.
Bye, guys.
Bye.